Welcome to the another session in Frontiers in CFD. So today we are going to do the CFD analysis of staggered lithium-ion battery modules with the phase change material, and the casing of the cells are been provided with the hexagonal fins, and this is for your effective thermal management. So the first objective is to design the geometry of staggered lithium-ion battery pack with integrated hexagonal fins and having a phase change material for the thermal management. So to generate the high quality computational mesh for the battery pack, ensuring the appropriate element size and boundary conditions which is required to be done in the setup part. So to perform the simulation and visualize the contours of liquid fraction, contours of total temperature of system, and so on. So this is the reference geometry that we are going to follow. This is not the exact geometry, but in addition to this we'll be having a kind of fin structure. So the base diagram is this. So this is how the fin structure that will be. So around the cells, as what we are observing in the earlier image, so we are having a kind of casing, and around the casing there will be a fins kind of arrangement which is provided. So this is kind of hexagonal element. Each side has the we can say side having 2.5 mm thickness, and we say from the center to the center of this hexagonal portion, it is the distance is 16 mm. So accordingly we are proceeding for the simulation part. Welcome you all to another session on Frontiers in CFD. So today we are going to prepare one of the simulation which is related to the configuration which has been shown over here. We might not be using the exact the similar kind of fins arrangement, but the one of the basic idea we are taking from this reference, and accordingly we are going to proceed. Okay, so let's proceed with this is one of the basic dimension that we are going to follow. So let's click on Workbench window. So we'll start with the Workbench and we'll generate the geometry in Fluent. So this is one of the basic dimension which we are going to follow for centers. Along with that, uh, we have some slight changes in the dimensions in terms of here we have some T section. Instead of a T section, we are going to use some hexagonal uh, we can say fin structure. So this is one of the reference which we are taking, and accordingly we'll proceed. So let's click on Fluent. In Fluent, select the geometry. I will select the new design modular geometry. So first of all, the outline which we will prepare is this one, 98.35 and 216. So that's for this we might need to create a box. So let's set the units first to millimeter. So create, go to the primitive, that is not cylinder. I will start over it. Okay, first of all set the units to mm, set, then file, go to the create primitive, that is a box. So the dimensions, instead of add material I will make it add to frozen. So the x component I will take it 216, z component I will say take it 98.35, 98.35, and the y component I will take it 65. So accordingly we will proceed. So this is the first geometry which is in the form of box has been created. Now we need to actually generate this kind of circles. The distance between the two centers of the circle is 36, and the diameter is slightly different here, so that is 26 mm will be your diameter. So accordingly we are proceeding. So this is the distance 18, this is the distance 18. So I will preferably go with the ZX plane, and on that ZX plane I will create a sketch. So first of all, draw a circle here. So dimensions of the circle from one end I will take, this is here. So this is your 18. Similarly from the other end we'll take the dimensions, so that is also equal to 18. So diameter of the circle is 26. So this is what the first circle that is been generated. So this is one of the reference. So the distance between the two is 36 and the angle between them is 60. So accordingly we will proceed for the second and third cases. So what I will do, I will just try to draw a vertical line here. So dimension should be equal to 36. So put it 36 here. Second line which I will be having is from here to this. So dimensions, first of all I will go with the angular one. So this is the reference and this is your so I need angular dimension first of all. Okay, so this is one I need 60, so put it 60. Next I need the general dimensions for this, so this is again 36, so put it 36. So the first circle we are done, one line is also been drawn. So next is from this again I will draw one vertical line here, so let's take it 36 again. So each and every dimension we will put and then only we will proceed for the next step. So this is again 36. So one more line we require. So take dimension that is equal to 36. So let's draw. So carefully you have to do so that the point should not miss. So take it 36. Okay, so as for the diagram here 1 2 3 4 5 6 total we have 6. One is done, second, third, fourth, fifth and sixth. So accordingly we will draw the rest of the one. Circle again with the same diameter which same radius or diameter which we were taken earlier. Okay, so we are done with these circles. Similarly we will draw one lines here was in this direction. So this is your 36, so put it 36, then one more line. So this will be one more line here which is on this direction. So dimensions of this line will be again 36, so I'll just put it 36 here. The angle made by this line again from this uh, so the angle with respect to the horizontal is 60, so accordingly we have to take. So let's say this line makes an angle with respect to horizontal, so this should be equal to 120. So this two centers will be there. So one by one draw lines here from this to this. So this is also to be equal to 36. So carefully you have to take all the distances. You could have drawn by considering the cylinders also. Uh, so but you might have to take the distances for each time. So instead of that, better way to go with the sketch option. So one more time take the dimensions. We required only 5 here, so we'll stick to this only. So one more time here again you can actually copy all the circles at this location, and that is also one simplest way to proceed, but I will just draw a line. So draw the line. So we have drawn all the lines. Now it's time to draw the circles. ensure the circles are drawn correctly. So all the circles are been drawn. Now I will just trim out the unnecessary things which are not required for us. So for the purpose of drawing the lines in is to make it sure that the distances are same and the things are done accurate. Somebody might have used the copy options also. That is also one shortcut we can do. But copy option sometimes it make an error in terms of uh, intersecting edges or additional edges which are been present. So that may create some time. You might not be in position to extrude if some edges are been there. So this is what we are done. We have prepared all these cells. Now what I will do, I will just do one operation which is called as extrude. So click on extrude, make it apply. Instead of add material, I will make it slice material now. Depth I will take 65. So you can just check it out, the depth. Now let's make it generate. So as soon as you make it generate, you will see the cells are being generated and you can see individual cells are differentiated with respect to the pack. Now the first thing which we are done is just as per the geometry which is specified here. So we are done. The rest of the task is actually to prepare a kind of fin arrangement. We are not going to follow the T section. We are going to use some different arrangement, that is in terms of the hexagonal one. So what I will do, I will prepare one more sketch. So this sketch one, now I will go with the sketch 2. So what I will do, I will create a circle in sketch 2. So draw a circle. So the diameter now it will be different than the one which you have taken earlier. So it is like a casing which is also acting. So this will be equal to 28, and with this now we will proceed for the remaining. So we'll just focus on the first thing as of now, and then we'll do it for the rest. So first of all, draw a line from the sketch again from the center. So this is one of the line I had drawn. So we have to draw some kind of we can say hexagonal parts. So next part is to create the hexagon as I said. So let's give the dimensions to this line. So I will put it 16. So we require a specific angle of this line with respect to the vertical. So we'll use the same 60-degree angle, and we want angle here. So put it 60. Now we will create a hexagon. So I will say a polygon option here. So number of sides are 6. So we'll go with this arrangement. Let's make it horizontal. Okay, so the dimension we have to specify. So I will specify this as is equal to 2.5. So just check it on this side. So we have created a hexagon over here. So we need this similar arrangement on this side and this side. So total 4 we require. So what I will do, I will do with the option which is called as copy now. So this one I will select. This all sides I will select. Okay, so make it in paste here, and I will rotate it. So what should be the angle? So it is showing 90 here. I don't want 90. Actually I want 60, which is separation out. So make this is equal to 60 for example. Okay, so I will end this and I will one more time do the selection. Now the angle is set, I guess. So select this, this and this. So create copy, set the paste handle. Now shifted by 60. So I will select rotate by R. So it is here. So I don't want it here. Now it is here. So this is the point, the required point I required. So one more rotate by R. So I will require it here. So one more point rotate by, okay, so this is again rotate by R. Okay, so this is done. This is not correct, so we required a different one. So I will just end this and I will delete this part because it is not correct. So now select this one, this one, this one, this one. Now make it copy. Set the paste handle. Now I will shift it by. Now it will come correct. Okay, so this is now it has been generated. So this is as per the required direction. So I will make it end now. Now I will trim out the things which are not required for us. So go to the modify and click on trim. So whichever is not required, this will trim it out, the unnecessary parts. This is not required, this is also not required. So slightly zoom in so that there should not be any error in removing the parts. Okay, so this is removed. Similarly, on the other side also we have to do. So this is not required, this is not required, this is not required, not required, not required, this is not required. These are the two lines again not required. So we are done second part. Similarly, I will go with the third part. So now again remove the things which are not required for us. Okay, so we have removed the part. Similarly, we have to do it for the last one. Okay, so unnecessary, which are those unnecessary that only we have to remove. Okay, so this is one more. So the sketch has been done. Now you can just check it out once to ensure the things are correct. So I'll just try to do extrude operation with the help of sketch 2 and make it slice and just check it. If this comes correct, then we can do it for the others. So again I will go with the sketching option here and I will click on copy option now. Select copy. Now carefully you have to select all, sketch. So don't forget to select each and every layer because this may create errors later on. So the same thing we have to do it for all remaining layers. So I'll select copy option. Okay, send, this is the center. Ensure the geometry is correct or the sketch is correct. Okay, just a minute. Ensure you are selecting all. Do it in the proper way. Okay, select all. Not the point you have to select, you have to select the lines. Okay, ensure this all are selected. Copy, then here put it here on. Okay, so all the required places you have to fill it. Okay, so I'm not going to fill it here because I want with a different angle. So I just shift it, let us say rotate by, so this is not the required direction. One more time rotate, this is also not the required direction. This is not the required. Okay, just a minute, rotate by R. Okay, now I will flip it by horizontal, let us say. So now this is not the required direction, so I will just end it, and now I will do, first of all we'll do this operation for this extrude generate. So this has been done correctly for all the bottom layers, you can just check it out. Okay, now left with this one, so I will generate one more sketch 3. Now in that I will just do copy operation for, okay, so do the copy operation, select all the outer layers. So select this copy, so select the rotate by, okay, so this is not the required one, I will just make it say 30 and just check it out. Okay, so one more time I will select, now I selected the angle 30. Okay, so copy, set paste handle and rotate by R. So one more time, so this is the required direction. So this is the first place, this is the second one, this is the third one, fourth one, this is come, and this one. So we have done it for all. So click on end option, and now one more time do the extrude operation for sketch 3, make it apply and select slice material and then generate. Now you can see all the layers are been generated. So this is your the PCM portion, this is your cells, and this is your fins arrangement. So accordingly now we'll do the name selections for each and every layer. So one by one I will do. So first of all I will form part for the cell. So select all cells and form the part. So let us say form new part. I will denote this as cell. Okay, so this is your PCM. So I think it will be the first option. Yeah, so this is PCM, so specify PCM. Now select casings, all casing I will select, sorry, casing along with the fins. So we'll select, sorry, not this. So this is also has to be form new part. Okay, so form new part, we'll put it as the fins. Okay, so fins with casing. So this is your PCM, this is your cells, so denote all of them as cells. So let's say copy, put the name at each and every place for your cell. So rename each and every one with the help of cell. So I will specify the name, that is cell, or at all places. Okay, so this is the cell has been defined. Now you have to go with the fin with casing. So we have to rename it for all. So one by one we'll do this. Why we are specifying the name? Because we don't want too many boundary conditions in the end while doing the setup. So that's why this is done. Okay, so this is what the fins with casing, the name has been defined. So PCM, ensure that this is solid. Then cell you are having, so ensure this is also solid, and fins with casing. Ensure each and every place you have given the name as per the what we have specified right now. So now let's save the work. So click on that. So prepare a separate folder. Say hexagonal fins with casing, and the number of cells which we are having are 17. So save this, copy address and put it here. Okay, so the geometry preparation has been done. Now you can actually close the design modeler. So let's proceed for the mesh. Click on edit. Okay, so due to Windows update, this error has been showing. I will just click on clear generated data here, and then I will close the meshing part, and one more time I will open the same meshing here. So go to the edit. Now the window will appear as it is. So this might be the issue when you are running this ANSYS. So fit to window, make it here. So I will just generate the mesh first as a default mesh. So the computer at its own will generate the mesh. So this may not be that good for us. So I will go with some finer size of mesh. So statistics you can observe it is 60,000. So I put it 0.005. Let's make it generate. Okay, so not much variation. So I will put it 0.001. Let's see how the mesh changes. So we also need to take into consideration the number of nodes and elements. So accordingly we will proceed for the next step. Always take a look at the memory usage we are having. So we have generated the mesh. So this looks to be a better one. If you want, you can actually make it further fine also. So this is 2537475. So this is the number of nodes and element which is available as of now. You can make it further fine. It's depend on your capabilities with your computer. So I will preferably will keep it with this only, and I will proceed for this part. Okay. So this is with your PCM. So what I will do, I will just go to the geometry and we'll see select cells. So hide all other bodies, and now I will select all the faces. So this will be useful for me in order to know the cell temperature. So that's why I am doing this work. So mention this as cell boundary. So create name selection. I will put it here as cell boundary. So I have specified the name, that is cell boundary here. So I will make it show all bodies. Okay. So similarly, fins with casing, if you want, you can select all, and accordingly you can also, let us say sometime you want to specify the convection. So in that case, this is one of the option which we can go for. So hide all other bodies, and I will select all the faces. So carefully you have to select all faces, because ultimately this will I will make it select all. Let us say I selected all. So these are the faces I selected. I'm deselecting some of the faces which are been there here. So I selected all, and then I am deselecting the internal faces only. I will keep it with the outside one. Okay. So I am deselecting this outer faces. So here. So you can see all the outer faces are selected. So this is what we were expecting. So I will put it create name selection. I will see specify this is convection casing fin, convection from casing fin. So or I can reduce the name convection casing fin. So let's make it okay. So this is what I have selected. So show all bodies now. The PCM which is already there with us. So this is PCM, and then we have fins and casing. So let's click on update, so that the solution will be updated. So you must see the mesh translation to Fluent successful message. If it doesn't appear, you have to go with the further finer size of the mesh. If it doesn't appear, but if it is appears, as you can see here, So we can actually proceed for the next step. So let's close the meshing part now. Okay, so next step is your setup. Click on edit. So click on double precision. So I will put it 16. Let's click on start. So this will take some time to load. So accordingly we'll wait, and once the object is loaded, we'll start back. So the object is loaded. Now we can proceed for the next step. So specify transient gravity minus 9.81. Model I will select energy equation has to be turned on. Viscous K epsilon enhance wall treatment thermal effect curvature correction. Let's make it okay. Then solidification melting, you have to turn it on. Make it okay. Here. Then materials. So we don't have air present, so I will rightly put it here, the paraffin wax. So the properties we already have for paraffin wax. So density is 790, specific heat is 2150, thermal conductivity is 0.22, viscosity is 0.01, pure solvent melting heat is 240, 800, solidus temperature is 313.6, liquidus temperature is 317.6. So make it change grade. Okay, so this is done. So for solid, we'll put first lithium batteries. So the properties of lithium batteries, we will take it from the reference paper. Here there is a different material has been used as a PCM, but we are using paraffin wax. So battery properties will use the same, which is specified here. So the battery properties are 2962.4, thermal conductivity will be equal to 30, and specific heat is 970. So as per the paper, we are following this dimension. So let's make it change grade and okay. So this is done for lithium batteries. So next is one more solid I will add, that is aluminum. So make it copy and then close. So I will just add this material here. So PCM solid, I will put paraffin wax solid. So here also we'll put paraffin wax solid. So the density of the paraffin wax solid is 880, specific heat is 2000, and thermal conductivity is 0.2. So this is done for the paraffin wax. Okay, so next is the fin material. So again I'll go with the database. So one more time, let's click on aluminum, make it copy and then close. So here I will make fin and casing. So here fin and casing. So as for the paper, we have some properties. So we are going to follow the properties. So this is 2719. This is specific heat is 871. So this is same, and 202.4. So as for the paper, they use it for aluminum. So the same metal, same we are putting. It is for actually aluminum. So we don't need to make any change over here. So make it here we are just changing the name, fin and casing. So next is cell zone conditions. So zone types. So cell, it is your solid. So I will make cell as solid. So you need to change the name, material name here. So this is your lithium battery source term. So we will provide the heat generation per unit volume. So as per the paper, there are three different values. So 2C, 3C, 4C. So preferably we'll go with the value which is slightly on the higher side. You can go with 3C, or also you can go with the 4C. So we'll go with 3C, that is 222984. So I'll put it here, 222984. So we are going with the 3C values, and we are going to proceed with this. Okay, so PCM again, fins with casing, I will change it to solid. So fins and casing, that is same material. You just need to click on apply. Okay, so we will keep the PCM as a fluid only. I'm not going to change it here. I will keep it paraffin wax only as it is, because the wall boundary conditions already have PCM solid. So that's why we are defined here PCM as a fluid. So next is your, okay, so now next cell boundary contact regions, whichever you are observing, you have to ensure that these are all lithium batteries. So if they are there, so you don't need to make any changes. So by default their option is available, so you may check randomly. So for this, by default the material is the lithium batteries, so you don't need to check anything as far as these things are concerned. But if you change, let us say if it is different materials available, so in that case you have to check it. So this is cell boundary contact region. Convection casing, so you need to check it once, because it may show you lithium batteries as a default option. So convection casing, I will select fin and casing. So this is what you have to do it for all, wherever it is mentioned fins and convection fin and casing. So you have to do some changes over there. So fin and casing, the option I am going to select, make it apply and then close. So wherever you observe the convection casing, so that material you have to select as the fin and casing. In cell boundary contact region, by default the option was available, so it was not necessary to select. So fin and casing, make it apply and then close. So you have to do it for all wherever you are observing the convection and fin and casing. Additionally, if you want to put some convective heat transfer coefficient, you can also put here. So this may be slightly a lengthier process, so but you have to do this for each and every layer. Otherwise your definitions might, and the results might deviate. So carefully select for each and every case fins and casing. So we have selected it for all. So let's make it apply and then finally close it. So few things will be remaining. So we have to see here. So wall cell. So this is lithium batteries, by default option is there, so you don't need to select wall fins. So here you have to select wall fin and casing because default option will be lithium batteries. So PCM. Okay, last one is wall PCM. So here you have to select the solid material. So here paraffin wax solid, make it apply and then close. So we have done it for all these cases. Now we have to go with the report definition. So click on surface report, area weighted average. So temperature, I will select total temperature, print to console. So here I will put total temperature report definition. So I will select system, report definition 0. So I will select all the layers and make it okay. Okay, so this is what we have done. Now next step is to select the temperature of cell, but here it is slightly uh, we can say as the things are not visible. So first I will prefer to go with the animation and then I will go back to report definition again. So click on initialize. Okay, we have done the initialization. So autosave I will put it to 20. Go to the solution animation. So inside the solution animation you will say, first of all I will select temperature. You will select total temperature. Go to color map option, instead of exponential select the float scale, make it apply and then close. Click on okay, so select all and click on total temperature of the system, then close this, select the contour. Here mention total temperature system. Okay, so total temperature system animation, make it okay. So we have done it for total temperature system animation. Now I will select cell temperature animation. Okay, so go to new object, contours. So temperature, total temperature. Now I will select all cell boundary contact regions. Okay, so I selected all cell boundary contact region and then I will select wall cell at bottom. So go to color map option, select float, make it apply, then close and save display. So now you will be able to see each and every cell. So contour 2 I will select. Okay, so make it save display and then close this. So here I will make it cell temperature animation. So earlier was animation 1, I will put it this as animation 2. So make it okay. So this is for your cell temperature. Next thing is the solidification melting. So new object, contours. So I will say solidification melting liquid fraction. Now where the liquid fraction is visible, so it should be what PCM. So first of all I'll select PCM. Instead of color map you say take float, make it apply, close, save display. So right now it is not properly visible, so we have to select few regions which are related to PCM. Okay, so I take the contact region on one side. So okay, zoom in properly. Okay, so first of all I select the contact region SRC, just check if someone has. Okay, so you can see it is here, it has came here. So 10 SRC, 10 is also there, 11 SRC is also there, 12 SRC is also in there, so 13 SRC, okay, 14 SRC, so one by one you have to check it, which one has appeared, which one has not appeared. 15, so here 16, I'm not sure which is the 16, just check it once. Okay, 16 is also there, 17 I'll just do, then just check 18. Okay, so I will put skip 18 as of now. Contact region 2 SRC I will put. Okay, so 2 is also there. I will put 3 also. Okay, so 3 is also appeared. I will put 4 SRC. Okay, 4 is also appeared. 5 will also put. Then 6. So 8 is also done. Okay, so we are done with 9 also. So you will see all contact regions are been selected now. The PCM is also visible in better way. You can just check it out. So you just have to remember these names whichever we have selected, contact regions SRC which we have selected, so that you have to remember. So you may note it down, contact region SRC which we have selected. So first of all SRC, then 10 SRC, then 11 SRC, 12 SRC, 13 SRC, 14 SRC, 15, 16, 17, then 2 SRC, then 3 SRC. So you have to remember which you have done. 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. So all these SRC regions we have to select. Okay. So this is done for the PCM part. Ensure the scale is float. Make it save display and then close. So contour 3 I will put it liquid fraction. Okay, so liquid fraction I will put animation now here 3. So let's make it okay. Now what I will do, I will go back to report definition, surface report, area weighted average. So I will put solidification melting. So contact region SRC I will select 10 SRC, 11, 12, 13, 14, 15, 16, 17. Then 2 SRC, 3 SRC, 4, 5, 6, 7, 8, 9. So print to console and so I will put solidification melting. Okay, so report definition that will be equal to, let us say 1. Solid phase melting, I will put it curve. So report definition 1. So let's make it. Okay, so one more thing which is required, wall PCM. Select all. Okay, so this is done. Next is your cell temperature. So here total temperature. So here total temperature. Now we are dealing with cell. So select wall cell and select cell boundary contact region. So all cell boundary contact region you have to select here in order to proceed for the next step. So here I will put cell temperature curve. So report definition I will put it as 2. Okay, so earlier was 1. So let's make it. Okay, so we are done with 3 report definitions. So cell temperature curve, solidification melting curve, total temperature system curve. So this is the 3 curves we are having. One more time, just I will go and check the uh, liquid fraction. So here I will just see if I select it properly. Yeah, all PCM is also selected. Okay, so this is done. Now you have to go to the run calculation and you have to click on number of depths. So I will put it 10 initially and I will run the calculation. So this may take some more time, and the iterations, after performing 20 iterations, you will be able to see all the 3 animation which we have set along with the 3 report definition which we have set. So this we have to wait for around 20 iterations in order to visualize the curves as well as in order to visualize the animation windows. Initially you will see the liquid fraction as of now on the screen, that is showing 0 because the process is just started, and initially the PCM is in the solid form, so you don't have any liquid present. So initially it will show you all the liquid fraction that is equal to 0. So once it reaches to the temperature which is related to the melting, so that time you will see the liquid fraction is actually changing. So till the time your system temperature doesn't reach to the solidification and melting temperature which we have specified during the materials, so till that time you will not see any kind of liquid fraction present over there. So we have to wait for the liquid fraction, but after performing 20 iterations you will be able to see 6 windows, 3 are for animation windows and 3 for your report definitions. So all these things will be visible after performing the first 20 iterations. So once the 20 iterations have been completed, you will see the window which is appearing. So we'll take a quick look of the window which will appear. Now 12s are completed, around 10 are left. So once that is done, you will see all 6 windows available. So you have to run it further till the time you don't reach to the solidification melting, and you will see the curves also. So this is the as per the paper, as I said earlier. So we have followed the intermediate value 228984. Sorry, 222984. You can run it for 4C or you can run it for 2C also. So depending on whichever the case you are considering. So let me clear one more time. We have took the battery material here. We have used paraffin wax as a material, and this is we have used the FEEN material. Apart from that, we have used the heat generation value also, and this is the sample uh, schematic diagram which we have followed. Actually we are not using a kind of a rectangular shape arrangement over here. We are actually using some different arrangement, as you are aware. In the it is kind of hexagonal channels, hexagonal sections we are considered. So this is what we have slightly different, we can say the model as compared to the previous paper, but ultimately we are following the properties of battery along with the properties of fin material which we are following. Otherwise the PCM we are considering the paraffin wax here. So you can see now windows are visible. So again, this is at the preliminary stage. You can see the cell temperatures. You will see the PCM temperature over here along with the total system, and here the PCM not is again, as I said earlier, we haven't reached to the solidification melting point temperatures, so that's why you will see all the liquid fraction is 0. So this is the total temperature, cell temperature curve, which shows you the temperature of cell. This is the one curve which is flat as of now, as I said earlier. uh, till the time you are not reaching to solidification melting point, this will be a flat curve, and this one shows you the total temperature of system. So as I said, there are 6 total windows which are available to us, and that are useful for us in order to we can say understand how the system works with the special cases like here. So again, as I said, we are not specified any kind of convection coefficient. uh, so this is that color contours temperature for the cell, and still the liquid fraction is not present because we haven't reached to that particular point. So you may see the temperature scale on this side. So if we reach to that stage which we have specified during the material, that is 313 to 317.6. So till that time we are not reaching that, you will not see any kind of liquid fraction present here, as well as you will not see any kind of the curve which is going upward. So this is what we have to wait till the calculations, till the time we are doing the calculation, and till the time this temperature system goes to around 313 or 314, 312 to 317 Kelvin. So this is all about the simulation which we are running. Definitely it will take some long time, so we'll continue this in the background process, and we'll uh, take updates after some intervals of times. So we have completed around 50 time steps. So for the 50 time steps, you can see the temperature which has been visible here. The cell temperatures are slightly on the higher side. We are not observing any kind of liquefaction as of now, as the temperature hasn't reached to solidification and melting point. Then cell temperature curve, again it is rising. Solidification melting, it is flat as of now. As I said, it hasn't reached to that point. Total temperature of system, again it is increasing. So this is what we have done it for 50 times tests. We definitely have to run it for more number of times in order to visualize this uh, the results. So let's proceed further. So once the work is saved, we'll proceed further. We can say further calculations. So as you can see, what we are expecting is we are expecting this curve to get flat after some duration of time. Same way, this liquid fraction will go up, and this is also likely to get flat after some time. So this is what we are expecting. So the work has been saved. Now you can run the simulation. So we'll run it further for 50 time steps more, and let's visualize it after 50 time steps. So let's make it okay. So we are at the end of around 300 time steps and flow time. So this is 98% is completed. You can see the liquid fraction. Just now it has been visible. So okay, this is the liquid fraction which is visible. So this shows you the contours of total temperature of the system here. This okay, the calculation is complete. So the contours of total temperature of the system. This shows you the cell temperature. Then this shows you the liquid fraction which is now been visible. Um, the cell temperature curve, solidification melting, the curve just now has started. Earlier it was flat, as you can see in the previous section. This is also the curve which is going up. So that is total temperature of system. This is your scale residual. So what we can see out of here is the as we reach to a temperature around 314 Kelvin, we are able to see the solidification melting which is happening over there. So this is the curve also visible where the liquid fraction has been there. So again, still we need to run it further in order to visualize it in more better way, because over the period of time you will see this curves likely to get flat. That is total temperature of system and total temperature of the cell, they are likely to get become flat. So let's first of all save the work, and then we'll run the simulation again, and we'll just check it out the results maybe at the end of few time steps. So let's save this one more time, and let's run the simulation further. Okay, so I will just put it now somewhere around maybe around 50 one more time, and just start the iteration process. So we are around 400 time steps. So after 400 time steps, these are the contours of temperature. So this shows the cell temperature, and this is the liquid fraction which has been visible. You can see it is around 0.46. Then this curve is likely to become flat. So slightly it is becoming flat. So that is cell temperature. This is the solidification melting curve which we are having. This shows again the total temperature of system curve, and this shows you the number of the scale residual, where you can also observe the number of iterations which have been performed. So with this, I think we can run the simulation further in order to get the curves to be slightly more flat. So there will be some stage where the system temperature is not increasing beyond a particular value. So we might have to run the simulation maybe further to visualize these contours. This shows the total temperature of the cell, how it is varying. So you can see the end temperature. So this shows the total temperature of the system. You can see the heat has been dissipated to the PCM from the cell. So this image shows you the contours of liquid fraction. Right now we are not able to see, but after some flow time of 300 seconds you will be able to see the liquid fraction. So this is the chart which is obtained, liquid fraction with respect to time. So after 300 seconds, as I said, you will see the liquid fraction which is present. Then this shows the system temperature with respect to flow time. So system temperature is slightly below, just touching 316. Then this shows the cell temperature which is slightly going beyond 316 Kelvin.